Now we leave the stage to Emily Riehl, who will talk to us about challenges in auto-formalizing category theory. Emily's from Johns Hopkins, and please, Emily.
Great. Thank you very much. I'm very happy to have the opportunity to be here. So I guess I want to start by giving a little bit of a framing for this talk, which is meant to give more of a sort of big picture rather than introduce specific details about the category theory part of the Lean mathematics library. And potentially a way to frame it is as follows. So I think a lot of us are here because we believe in computer formalization as a new paradigm for mathematical proof writing, a new way to develop proofs in our own heads, communicate those proofs to others, to be used in pedagogy, experiments in teaching mathematics. And of course, there's applications of computer formalization beyond mathematics to formal methods, which are very important too. And in particular, in this room, there's a lot of excitement about potential acceleration of this paradigm with interactions with AI. So computer formalization as a paradigm has been around for quite a while, has a distinguished history, but there is some acceleration more recently, some of which is through network effects, through the work of developers who are creating new and better proof assistants, but also there's a lot of unquestionable potential with artificial intelligence. But the world of mathematics, or I guess the frontiers of mathematics have also been accelerating. There's a lot of exciting new developments in new areas. And a question that I've been thinking about a lot is how possible it is for this new paradigm of computer formalization to keep up with the research frontiers of mathematics, not just in some subject areas, but in all subject areas. If this is going to transform the way that mathematicians develop proofs, we need the tool to really be usable in all areas of mathematics. And in a sort of recent announcement, this is an article written by Talia Ringer that accompanied the Nature paper about alpha proof that came out last month. Talia contrasted the experience of different mathematicians who have been experiencing with AI. So she mentioned, Talia mentioned several people by name, and one in particular was Kevin Buzzard, who everyone here loves to quote. So what Talia said about, or Talia quoted Kevin, who said that he described that no AI system is anywhere near useful to me right now, referring to the Fermat's theorem project, because his development is full of what are called bespoke definitions that in his case were sort of are not necessarily in MathLib. So I think it's interesting to think about how Kevin's experience might contrast with experiences of others that have had more success in using these new AI tools. So that's intended as a framing for this talk. So what I wrote as the plan is the following. So I work in an area of mathematics called category theory, which is maybe relevant here as an ambassador from the sort of mathematics that seems to be a little bit more difficult to formalize than some other areas. I guess I'm not referring to category theory specifically. Sorry, I do want to make a distinction between sort of my the sort of category theory that I'll be discussing here and sort of the research frontiers in category theory, which I will not really be discussing here. So, category theory is a very well-developed library in MathLib. A lot of this is, been in there for, 5-6 years now. So this is an area where formalization and Lean has been very successful. But nevertheless, I think we can use it as a perhaps slightly more accessible illustration of some of the features of formal mathematics in certain subject areas that are more complicated to work with than you might think. At the very end of the talk, I'll mention a little bit about perspectives from higher dimensional categories, sort of infinity category theory, which is really kind of more of what I was thinking of in the framing and imagining areas where, formalization right now really lags very far behind current research frontiers. So anyway, I'm trying to make a point that's sort of more accessible here. So a thing that distinguishes category theory from other subject areas is the importance of the definitions. I mean, there's been a recognition in the field that the definitions are often the main theoretical advance in a new paper. What I'm hoping to illustrate today is that somehow the proofs can be easy because the definitions are doing all of the work. Category theory is this sort of abstract nonsense area of mathematics where you know so little about the objects that you're studying that there's only one argument that you could possibly make, and that argument gives to correct proof because the definitions were well chosen. So this talk has two parts. The first one, I'm going to get in the weeds and give an explicit example of a theorem from category theory that involves a lot of complicated definitions, but then the theorem itself has a very sort of follow your nose sort of proof. I am going to actually present the theorem and the proof in full detail because I can't resist. It's a beautiful theorem that I think is not quite as well known, but I'm going to try to describe it at sort of two levels. So in the first part of the talk, I will, for those who want to learn the details of the proof of this theorem, I'll be presenting it at that level, but I'll also be commenting on the proof as I'm presenting it. So if you want to tune out the mathematical details and try to follow the commentary, I'm hoping that this will be possible. And then there's the second part of the talk, I'm going to highlight using that example and another example that I'll bring in then some specific challenges for auto-formalization. So this will be more of a commentary on what the lean code around these sorts of definitions looks like. Okay, so that's the plan. Great. So, I mean, the whole field of category theory was really born from a definition. So the historical origins are in a 1945 paper by Samuel Eilenberg and Saunders MacLean. The title is General Theory of Natural Equivalences, and in a sense, the entire paper is to give, the whole point of the entire paper is to give a precise meaning to this term natural equivalence, where natural means something technical in category theory, but captures the idea that some construction is natural as opposed to making some arbitrary choices. Equivalence is in the sense of equivalence of types or isomorphism, if you know what that term means. And so I'm going to start by just giving this definition. So to define natural equivalence, more commonly called natural isomorphism, one must first introduce some other technical terms of categories and functors. So what is a category? So a category has a type of objects and a dependent type of arrows with composition and identities. That's further data and then satisfying certain axioms. So what I've cobbled together here is the definition that appears in MathLib. It's really sort of split across some structures that extend previous structures. Let me just give some comments on it. So firstly, the definition of a category involves two universe levels. That's the U and the V. This is one of the headaches that you have to deal with when formalizing category theory is not all your types live at the same universe level. So obj here is the notation for the type of objects. And then the central data of a category is what in other settings of mathematics you might call a directed graph or a quiver. So whenever you're given two objects, there is a type of arrows between them. And that's this dependent type HOM, which is the first line of this definition. So given two objects, we have a type of arrows between them. There are two notations in MathLib for this type, kind of mirroring some notations that are used on paper as well. So if X and Y are objects, HOM XY refers to the type of arrows from X to Y. The name HOM comes from the term homomorphism. But MathLib also uses this sort of slightly longer arrow as a synonym for that type. So if you have the shorter arrows that appear in this slide are the functions, the symbols for function types. The longer arrow is the symbol for the type of arrows or homomorphisms in a category. I've mostly suppressed it from the slides, but it will appear in kind of the natural language here. Okay, so that's the basic data of a category. It has objects and arrows, and then category theory is all about composition of arrows and the sort of further axioms. But let me move past that. So part of the philosophy of category theory is that any sort of mathematical object should be studied together with the arrows between two related mathematical objects. And that philosophy applies to categories themselves. And so in particular, between categories, we have a notion of arrow, and these are called functors. So it's a mapping between categories that sends objects to objects and arrows to arrows while preserving all of the structure. So preserving composition, preserving identities, and so on and so forth. So here, given two categories, so C is a type together with a category structure. D is a type together with a category structure, as in the previous slide. Then the data of a functor involves, firstly, a mapping on objects, so a function that carries an object in C to an object in D. Then a sort of dependent function on arrows. So for every arrow in C, I have a corresponding arrow in D. But the use of the dependent types, so the arrows we consider as a dependent type over the objects, means we can say directly something that would otherwise be an axiom, which is that if you apply the action of a functor to an arrow, it needs to respect the source and target objects. So if I apply the functor to an arrow that goes from X to Y in C, then its image in the category D goes from the functor applied to the object X to the functor applied to the object Y. So that's indicated by the typing of this field map of the structure functor. And then there are axioms about preservation of identities and preservation of composition. Okay, let me pause and discuss some mathematical examples of functors. So here in the sort of green cyan color, I'm referencing two categories. So the first is the category of rings. This is a sort of mathematical structure that I guess we saw something about in the number theory talk this morning. So rings are, objects that have an addition and a multiplication satisfying various axioms. Those are the objects in the category of rings, and the morphisms in the category of rings are something called ring homomorphisms that preserve the functions that preserve the multiplication, the addition, and also both the additive and multiplicative identities. So then type refers to another category whose objects are just types and whose morphisms are functions. In a different talk, I would refer to that category as set, but here I'll call it type. And the first example that I want to mention is a construction that sends a ring to its type of units. So these are the elements of the ring that have multiplicative inverses. So for example, so to say something is a functor, that means firstly I need to have a mapping on objects, and then I need to have a mapping on arrows, and then I need a whole bunch of axioms. So the mapping on objects, for example, so there's a ring of integers. In the ring of integers, there are two elements that are invertible with respect to multiplication, plus and minus 1. So this functor acts by sending Z, the ring of integers, to the type that is comprised of just the two elements, 1 and minus 1. So similarly, there's a ring Z mod 3, which has three elements, 0, 1, and 2. 0 is not invertible for multiplication, but 1 and 2 are. So the units of that type are the set 1 and 2. And then what makes this construction functorial is that I can extend it from a mapping on objects, sending a ring to a type, to a mapping on the arrows as well. So here I've illustrated by considering, drawn vertically, one particular ring homomorphism. So there's a ring homomorphism from the ring Z to the ring Z mod 3 that takes an integer to its equivalence class modulo 3. It's a surjective ring homomorphism. And so functoriality says that that construction has a corresponding construction on the units in the ring. So if I apply that homomorphism to an element that has a multiplicative inverse, I get an element that has a multiplicative inverse. So there's a corresponding function. And indeed, it sends 1 to 1 and minus 1 to 2 on the elements. Then there are further axioms. I need to check that this operation respects composition and identities. But that's the key idea of a functor, is it's a mapping on objects and then also a mapping on arrows that respects the source, targets, identities, and composition. Okay, so that was the first example of of a functor. And then the second one I wanted to discuss is more abstract here. So C can be thought of as being an arbitrary category. And A should be regarded as a fixed object inside that category. And then if I had another object in the category X, I can form the type hom AX of arrows in C from A to X. So this is a construction that takes an object in the category C, namely X, to an object in the category of types, namely the type hom AX of arrows from A to X. And again, this operation on objects of categories is functorial. I can extend it to arrows. So if I have an arrow from X to Y in C, which I've displayed vertically, I get a corresponding arrow in the category of types, namely a function. And that function is just given by composition with F. So if I have an element of the type hom AX that is an arrow from A to X, I can compose it with my arrow F from X to Y and get an arrow from A to Y, and that's a function. And again, this mapping is functorial. So those are two examples of functors between categories. Okay, so this is all intended to build up to the definition of natural transformation, natural isomorphism. And we have these categories that contain objects and arrows. We have these functors, which are the mappings between categories, really the arrows between categories. Natural transformations then can be regarded as mappings between functors or arrows between functors, with a caveat that the functors need to be parallel. So natural transformation only makes sense when we have two functors that have the same source category and the same target category. So here again, I've copied the mathlib definition. So F and G are both functors from C to D. And then we have a notion of a natural transformation from F to G. And this definition, again, involves some data. So the data are what I would describe as the components of the natural transformation, and that's given by this first field, app. So app is a function that takes an object X of the domain category C and then returns an arrow in the target category D from F of X to G of X. So from the application of the first functor to the application of the second functor. That's the essential data of a natural transformation. And then there's a condition that this data must satisfy, which is something called naturality, that I'm not going to discuss at all today because in the proof that we'll give, it doesn't actually appear. It's then actually required to be checked by something to do with the innate lemma. In any case, let's give an example. So on the previous slide, I mentioned two functors from ring to type. The one on the bottom is this functor that takes a ring to the type of units, the type of multiplicatively invertible elements. The functor on the top is an example of an instantiation of the second example. So within the category ring, I have an object which I've written as z brackets x comma x inverse. This is the ring of Laurent polynomials. It's a particular example of a ring. And then I have this notion of a functor, which is hom from that into an arbitrary object. This is the functor that would take another ring R to the type of ring homomorphisms from the Laurent polynomials into R. And so these are a parallel pair of functors. So I could consider a natural transformation between them. So on the right, I've illustrated the data of a natural transformation. So a natural transformation, the components involve for an arbitrary ring R, an arrow in the category, in this case of types, from the application of the first functor to the application of the second. So I need a function that goes from the type of ring homomorphisms from Laurent polynomials into R to the type of multiplicative units in the ring R. And there is such a function. It sends a ring homomorphism phi to the element that you get by evaluating at the element X in the ring of Laurent polynomials, because X is a invertible element in the ring of Laurent polynomials. Then this phi of X is an invertible element in the ring R. So this is an example of a natural transformation, and in fact, it's one of these natural equivalences or natural isomorphisms referred to in the Eilenberg-MacLean paper. And the reason is because that mapping between types is an equivalence of types or an isomorphism in the category of types. This is not obvious if you haven't seen this before, but it's something that you can check. Okay. So the reason for those particular examples is this is an example of a notion of co-representable functor, which is the first of the main definitions that's going to appear in the theorem that I will state on this slide. So let's consider now an arbitrary functor from an arbitrary category, but valued in the category of types. So we'll say that that functor f is co-representable if it is naturally isomorphic to one of these functors of the form ham a blank. So a again is a fixed object in the category C. Ham a blank is another functor from C to type. And if f and this ham a blank, if those two functors are naturally isomorphic, so there's a natural transformation with invertible components between them, then we say that the functor a is co-representable. And the theorem whose proof I want to illustrate is a characterization of co-representable functors. It says, gives a condition that determines exactly when something like this exists. That condition is stated in terms of something called the category of elements of F. So this is a category built from F. And it says that the functor is co-representable if and only if its category of elements has an initial object. So the category of elements is again a category that can be built from a functor that is valued in the category of types. So to define a category, I need to tell you what the objects are and what the arrows are, and then some other structure that we're suppressing now. So the objects in this category are given by pairs, where the first component is an object in the category C, and the second component is an element in the type f of x. So that data together defines an object in this category of elements. And then an arrow in the category of elements between pairs of this form is given by the data of an arrow in the category C, satisfying the condition that when I act via the functor f, so now I have a function from the type f of x to the type f of y, that function is required to carry the element x to the element y. So under those conditions, the arrow in the category C defines an arrow in the category of elements. So the final thing to explain is this notion of an initial object. This is a definition that makes sense in an arbitrary category. And what it refers to is an object in that category with the property that for any other object, there is a unique arrow whose source is the initial object and whose target is the other object. So most objects in most categories do not have this property, but many categories will admit an initial object. And so that's the theorem. Okay, so that was the technical description. The high-level description is what I've done is I've given a bunch of technical definitions that are sort of non-obvious, and now I've stated a technical theorem. And what I'm going to illustrate on the next slide is that anybody could prove this theorem modulo understanding the definitions. So there will be absolutely no creativity involved in the proof of the theorem. The definitions will sort of dictate the obligations for each step of the proof. The hypotheses will give you precisely the data that is required to fulfill these obligations. And by just writing those steps one after another, we'll be able to complete the proof. You can imagine that this is the sort of thing that ought to be amenable to automation sort of exactly for that reason. And so that's the point that I'm going to try and make, the meta point, by giving this proof now. I want to make another point though. So this, I feel like there's a common fallacy that is invoked in giving mathematical talks, which is like, I can explain literally anything to literally anybody, provided I just give you all the definitions. So I want to acknowledge that I've just given you a bunch of definitions. And of course, if everybody has absorbed them in real time, then you have enough information logically to follow the proof. But I've been in the audience of many mathematical talks, and I understand that you don't actually absorb the definitions in real time. Okay. Anyway, with that apology, I'm going to do the thing anyway. And I'm just going to prove, so this theorem is an if and only if, and both directions exhibit this principle that all we're doing is following your nose, but I've just picked one of them. So we have time to do some other things. So in any case, what is the theorem again? It's a characterization of something called a co-representable functor. This is one of the technical definitions. In terms of category of elements, that's another technical definition. Having an initial object, that's a third technical definition. So I'm going to prove that under the hypotheses that the category of elements has an initial object, we can build this co-representation for the functor. And again, all the work has been done in stating the theorem and the definitions that are encoded in the theorem. There's no work to be done now. Okay, so what is this? So I'm proving an implication. So I assume that the category of elements does have an initial object. So that's giving me some data. That data is given by a pair, capital I, little I. Capital I is an object in the category C. Little I is an element of the type f of I. What I'm trying to show is that f is naturally isomorphic to some functor. The data of this, and the functor needs to be of the form hom a blank, where a is some object of C. Now, I have only one object of C in my setting, namely this object I, so I should clearly use that object to define the representation. That's one of these things. I mean, I'm really supposed to construct an arbitrary object, but I'm in a context where I only have a single object, so we might as well use that one. So in other words, I'm going to show that f is naturally isomorphic to the particular functor hom I blank. And so what do I need for that? So the data of a natural isomorphism is a family of equivalences between types. So I need to construct an equivalence between the type of arrows hom I x for any other object x of C and the type fx. So that's kind of all I need to do. If you're doing this in MATLib, essentially we've gotten this far by kind of unfolding definitions, and then there's a point of there's an existential quantifier where I'm supposed to supply an object of an element of a particular type, and I'm using the only element that I have. That's sort of all we've done so far. So very amenable to automation. Okay, so now I have a further obligation, which is to define an equivalence of types. So what is an equivalence of types? I need a function in one direction, a function in the other direction, and proofs that those functions are inverses. So the first thing I need is a function that takes an arrow from I to x. This is an arrow in the category C from I to x, and returns an element of f of x. So suppose little f is one of these arrows from I to x in the category C. So the other thing that I have in my context is this functor f, which converts arrows in the category C to functions between types. So I could apply the functor f to my arrow little f, and now I have a function from the type f of I to f of x. So I'm looking for an element of the type f of x. I have a function from fi to f of x. So I could apply that function to an element of f of I, and that would give me an element of f of x. And I have an element of f of I. That's the other bit of data, little I. So really, I'm just using exactly the data I have to do the construction that I need by the statement. So no creativity involved. Anyway, that's the construction of the function in one direction. So going back the other way, now I need a function from the type f of x to the type of arrows from I to x in C. So suppose I have an element, little x, in this type f of x. Now together my object, capital X, and my element, little x, defines exactly an object in this category of elements, which is referred to in the statement. And the hypothesis about my pair I is that it is initial object in the category of elements. I have not used that hypothesis yet, so I might as well use it now. What initial object means is that for any other object, such as this pair XX, I get a unique arrow from the object II to the object XX. So in particular, I get an arrow from II to XX. This is an arrow in the category of elements, but if you go back to the definition of arrows in the category of elements, the data of such an arrow is an arrow in the category C from I to X, which is what I need. So again, there's nothing here except using the definitions and the hypotheses to get the arrow. A priori, there's no reason to suppose this construction is the inverse of the previous construction, but again, these are the only constructions you could reasonably make in either setting using the data that's given. And indeed, they are inverses. So the other part of being an arrow in the category of elements is this specification that if I apply the functor f to that arrow and then evaluate it at the element little I get the element little x. And that's exactly the condition that shows that the second function is a right inverse of the first function, so undoes the first function. And then I need to show that the first function is a right inverse of the second function, undoes the second function, but that's where I use the uniqueness aspect in the universal property of initial objects. So not only does there exist an arrow from the initial object to any other one, but there exists a unique arrow. Uniqueness refers to an equality. in the type of arrows, and that's exactly what I need for this other condition. Okay, so that's the illustration of this proof. Okay, let's talk now about formalization. So what I've just illustrated is a theorem in category theory. I picked this theorem because I really like it. I feel like it's somehow, it's considered a relatively elementary piece of category theory, though it's not quite as well known as it should be. And in particular, it's not in MATLAB. So all of the definitions that I've referred to, category of elements, co-representable functor, initial object, these have been in MATLAB, I think since like 2019. So these have been in MATLAB for a very long time. But this particular theorem is not there. And so that means it's something that can be used as a test of the autoformalization capacity of a particular agent. So here I've stated these theorems in MATLAB. The first one is exactly the form that we've just discussed. The second one is something called the dual theorem. So the notion of a category gives rise to something called the opposite category, where I reverse the sources and targets of all of the arrows. And so there's a corresponding theorem referring to what are called contravariant functors, so those indexed by an opposite of a category rather than a category. So neither of these theorems are in MATLAB. But the proof of this theorem really involves, so now I'm going to go through some potential challenges in, I should say also, while this has not been formalized in MATLAB, it has been formalized by me, and the formal proof of the proof I just gave takes like 50 lines. So this is not a particularly difficult proof. I'm happy to show you. Let's say 50, but this is including like comments and lemmas and stuff like that, 50. So it's not very difficult, I mean, sorry, literally the file that has like all of the comments in it and stuff like that is 50 lines. So I don't know how many, okay, I should try to compress it. I mean, whatever. The point is that's not very much. Okay, so, and this is this version and also the version in the other direction and so on and so forth, plus some preliminary lemmas and so on. Okay, right. So, this came up a few times yesterday. This notion of being co-representable is a property of a functor. So in particular, the type that's in MATLAB that says that a functor is co-representable is a proposition. So is co-representable of F is a prop. And what is the proposition? The proposition is, again, that there exists some object X and C. I was calling this A before, so that F is co-representable by X. That means there's this natural isomorphism between F and the functor Hom X blank. But this co-representable by is really a type rather than a proposition because it involves data. So in other words, to prove that a particular functor F has this property is co-representable. So we just gave some sort of construction, and that construction involves explicit data. So firstly, you need to specify the object A. So that's some data, an element of a particular type. Then you need to specify the natural isomorphism. So that is this particular equivalence between types, which is again data, meaning the explicit functions that have to be inverses. That's kind of reflected in the prop value definition. It says that there exists some X and C so that some other type is non-empty, where this other type is this type F co-represented by A, which involves, again, the data of the explicit bijection. That was the thing that came up in the proof. And then also a proof of naturality, which did not come up in the proof because of something called the Yaneda lemma, which I don't want to discuss right now. So in other words, if an autoformalization is trying to prove this theorem just by unfolding definitions, it's going to get to the point where it has to construct explicit data. So we'll need some ability to work with Lean's definitions and not just its propositions. Okay. I mean, of course, it is possible to go back and forth between the proposition of being co-representable and the type that encodes this data of being co-representable by a particular thing, but there's a little bit of loss of computability. So if I know that F is co-representable by a particular object X and the particular natural equivalence little e, then that's exactly the data needed to prove the proposition that F is co-representable. But if I have the hypothesis, so that's this first code block. If I have the hypothesis that F is co-representable, and now I need to extract the data, I'm essentially using the axiom of choice to show I have a type that's non-empty and I need to pick an inhabitant. So what you'll see in the category library is that a lot of developments work with these types as if they were propositions, because if you stick with the types and not the propositions, you're carrying around the data and not forgetting it and re-choosing it all the time. So, as a hypothesis for a theorem, instead of hypothesizing that F is co-representable, I'll hypothesize that F is co-representable by a particular A. So I have using the data, I get to preserve the data in the construction rather than using the hypothesis. The first step would always be to choose the data and then get to the construction. So that's something you'll notice in the category library. And there's, a problem that was mentioned yesterday is that, I guess my understanding is several auto formalization agents are, trained to try and fill sorries if the sorries are the proofs of a theorem, but perhaps blocked from filling sorries if the sorries are elements of a definition. In category theory, that's really kind of blocking the best practice. Of course, I understand that if your sorry data, if you have a type and you're asking an AI agent to construct an arbitrary element of that type, then it might give you the wrong element. Just because you've called your type or your element Fibonacci sequence doesn't mean it's going to define the Fibonacci sequence and might define some arbitrary sequence. So I understand the theoretical problem. In other words, if we're asking an agent to construct an element of an arbitrary type, how do we know that it was the right element? But in practice, there are mathematical settings where that issue kind of disappears. One way to explain this is using a notion that comes from homotopy type theory of a homotopy proposition. And we can say that a type is a homotopy proposition, or it's a proposition if any two elements of that type can be identified. So if whenever I have two elements XY of type A, so maybe the one that I, the user, had in mind, and then the one that the AI agent constructed for me, those things are equal. So I can find a term in the equality type between X and Y. That's the notion of a homotopy proposition. So this says that it has at most one element. If there are no elements, then this predicate is trivially satisfied. But if I have two elements, then I can identify them. This type F co-representable by X, which is a type, is one of these examples. So in MATLAB, it is not a proposition. It's an element of type. It's not an element of prop. However, it is a proposition up to homotopy. So what this result is saying is that for any functor F, for any object X, if I have two elements here, so this E and E prime can be thought of as two different natural isomorphisms connecting these things. So there's, to explain this fully, I really need to get into sort of homotopy type theory and the notion of univalent category, which is something that I don't want to do. So there's maybe a small lie that you can talk to me about afterwards. But the conclusion of this theorem is then that E is equal to E prime. So the meta point that I'm trying to make is that there are certain settings where automatically generating data of types is less problematic when you would think. And category theory is one of those settings. Okay, so other challenges for auto-formalization of category theory involve kind of the API that's in the categories library, which is very well developed, but for that reason is rather complicated. So of the definitions I gave before, the one that is maybe the most elementary is this notion of an initial object, which I'll just remind you, it's an object of some category with the property that for any other object in the category, there's a unique arrow from the first object to the second object. This is one of the first definitions you often give in a category theory course. But if you look at it in MATLAB, it looks totally different from this. So what isInitial is isInitial is a property of X. So it's a predicate on an object X. and it's defined as being is colimit of as empty co-cone of X. Similarly, has initial, the property of a category that says it has an initial object is called has colimits of shape discrete. The zero here refers to universe levels, something called P empty of C. And so what of all of this is referring to? So these initial objects are special cases of this more general notion of colimit, which concerns something called an arbitrary diagram shape. In the case of initial objects, that diagram shape is something called the empty diagram. So it's sort of very trivial, but nevertheless, the sort of desire of the people who developed this in MATLAB, this was way before my time, is to work with this general limit colimit API. And what that means is there's a lot of simple definitions that if you look at how they've been formalized, it's through something way more complicated. And that makes them difficult to use. So again, there's sort of a well-developed API. If I had a particular, let's say we were trying to prove the other direction of the theorem, so that under the hypothesis that F is a co-representable functor, then this category has an initial object. So I have a particular object and I'm trying to show its initial. I'm definitely not going to show is colimit as empty co-cone. I mean, that's just not how in practice you think about an initial object. Instead, what I want to do is just check this sort of elementary property that was mentioned above, that for any other object there exists a unique arrow. That's sort of a more elementary thing to check. And what this last theorem is showing you is that you can conclude the presence of an initial object by checking the more elementary property that for any other object, the type of arrows from the initial object to that other one is non-empty. And then secondly is a sub-singleton. So that's the existence and uniqueness part of initiality. But you can see here, this proof is completely unreadable to me. I would absolutely not, I understand on paper how the elementary definition of an initial object shows that the initial object is the colimit of the empty co-cone. I could sit down on paper and explain that argument for you, but I could never produce this formalization that convinces MATLAB that this is true. And that's, I have kind of, it's not so clear what the pen and paper argument corresponding to this construction is. And again, this pervades the categories library. Okay, so this is kind of a silly sort of lower level issue. So as I mentioned before, that any category has an opposite category, which has the same underlying type of objects, but is defined by turning around the arrows. If you turn around the arrows twice, it's the same as not turning around the arrows at all. So the category C is equivalent to the category that results from doing this procedure twice, forming the opposite category and then forming the opposite category again. And then in particular, we call it a functor sort of covariant if its domain category is just an ordinary category, and we call it contravariant if its domain category is the opposite of some other category. But all categories are the opposites of some other categories. So are any functors covariant or contravariant? It's not entirely clear. I mean, it's clear that they're both. But of course, in practice, there are the functors that are covariant and there are the functors that are contravariant because they're the categories that are not opposite categories and the categories that are. I mean, this, again, I'm making, these are sort of logically contradictory statements, but nevertheless reflects kind of the deep feeling of mathematical practice. Yeah, so in particular, so I mentioned that this theorem has a dual theorem that also refers to the category of elements. But the way that the literature, and I guess myself prefer to construct the category of elements for contravariant functors is following a different convention that is used for the category of elements of covariant functors. In particular, the way that I would state the dual of this theorem is that the category of elements has a terminal object. So that's one, so there's a unique arrow to it rather than a unique arrow from it. That's different than the way this is stated in MATLAB because of these conventions, this sort of inability to decide whether a functor is covariant or contravariant. So to know sort of which theorem ought to apply. Okay, so another sort of autoformalization complication is a different issue that I'll explain using a different example. And this involves extending nested structures. So the first theorem I'm highlighting here because I've used the fact that it is missing from MathLib to design a test to give to auto-formalization agents. I have a second test as well, which involves a second theorem where the definitions are in MathLib, but the theorem itself is not. And this is that theorem. So it concerns something called a parametrized adjunction, which involves a functor of two variables. So here F is a functor whose domain is a product category, or really the way this is treated in MathLib, F is a functor that goes from the category A to the category of functors from B to C. So this is a functor of two variables, or a bifunctor. And what the theorem says is that if for each object of A, the induced functor F of A, that's now just the functor from B to C. So between the second and third category admits a right adjoint. I'm not going to define what an adjunction is, but it's some data associated to a functor, but this data can also be understood as a homotopy proposition, returning to the point we made before. Then those right adjoints assemble into a unique functor of two variables again. So the right adjoints G at some A are functors from C to B. As A varies, this extends uniquely to a functor on the category A op into functors from C to B. And this is unique so that this new functor of two variables has an underlying mapping on objects coinciding with the function that I've just described, and so that these isomorphisms are natural in all three variables. So I mean, the category theory in this natural language statement is maybe unfamiliar, but this is not that complicated of a mathematical statement. It just says, given some data, there exists a unique extension to some other data, where exists unique is in the standard sense of mathematics. But it turns out that this is rather subtle to formalize. So again, what this theorem is asserting is that, I have the hypothesis of a function that takes an object of the category A and produces a functor from C to B, together with an adjunction connecting between this functor and some other functor, again, for all objects A and A. Then from this, I get a unique functor of two variables, and here I've gone ahead and written it in the way that it would appear in MathLib. So this new functor G is a functor that goes from the category A op to the category of functors from C to B that's extending this given mapping. So I've given this natural language statement to the Gauss, which is the MathInc agent, and Aristotle, which is the harmonic agent. And they both sort of took different approaches to auto-formalizing the statement. And to be honest, it's not clear to me. I don't, again, this theorem is not in MathLib, so I don't have sort of a human written example to compare it to. A simpler version of this theorem concerning adjunctions of one variables is also not in MathLib. And I think it's just because this sort of thing is a bit awkward to express in dependent type theory. So the people who developed the theory of these adjunctions kind of leave this out. They achieve the same constructions, what you would get from the existence and what you would get from the uniqueness without ever stating the theorem that encodes the unique existence itself. That's my setting. I haven't talked to the people who developed this part of the library, so I don't know what they would say about this. But let's look a bit on these statements. So again, our hypotheses here are we have a functor, that's the F between three categories, a function, that's the thing I've written G naught, that takes an object in the category A and returns a functor from C to B. The hypothesis of some family of adjunctions, that's the turnstile symbol, that's the adjunction symbol. And the way that Gauss auto-formalized this statement is that then there exists a unique functor G, so that firstly, there exists proofs that for all objects of A, G acts on objects in a way extending the function G naught. So that was the kind of the first part of the statement, saying that this functor G should extend. One of the fields of the functor should be the sort of given extension before. Moreover, there exists adjunctions involving this new functor G and the previous functor. So essentially this adj field is redundant for the hypothesis HA above. Then something or other about naturality that's let's ignore. And then dealing with the redundancy between this HA and this ADJ, some statement involving a conjugate equivalence. That's the data of an explicit natural isomorphism involving these two adjunctions and the identity, natural transformation, and iktaham, which is kind of some device that's used in the category theory library to transport an equality between objects, in this case given by this hypothesis H of G, into an arrow. But the point again is, so if you're sort of sufficiently well versed in dependent type theory, you can parse this statement and connect it to the unique existence that I mentioned before. But if you're not sufficiently versed in dependent type theory, it's sort of less obvious, I would say, how this corresponds to the literature. So what Aristotle did was, sort of something similar, but in practice different. So you'll note their version of the statement doesn't use the sort of exists unique, which is what you might expect, but says the theorem is that from the given data, you can construct this functor G. You can construct what's called a parameterized adjunction between the F and G. So that's essentially this new ADJ field above. And then you can construct proofs that, again, the underlying action on objects of the functor G coincides with the function G0, that these adjunctions from the parameterized adjunction kind of transport along those equalities to coincide with the hypothesized adjunctions that we have previously. And moreover, then there's something called a heterogeneous equality between the parameterized adjunction that you've just constructed and one that is built from the extension previously. So again, all of this is coming from something blah, blah, blah. There exists unique extending given data. It becomes considerably more complicated in lean. Okay, and then the final thing I wanted to say is about some sort of what I like to call invisible mathematics. So the point of this previous result is it's about the unique existence of a functor extending given data is it's used in practice to construct these parameterized adjunctions, which are adjunctions between functors of two variables or two variable adjunctions. So these are where you have three functors involving three categories that are pairwise adjoint. Part of the reason for this as a test of autoformalization is that so parameterized adjunctions are in MATLAB, two variable adjunctions are not. So again, it can test the capacity to synthesize definitions. So I built an autoformalization challenge around these notions with involving the theorem that I just posed and a few others. And I included in there a lemma that I thought was going to be really trivial. And it turned out that this was one of the most difficult things to autoformalize. So this was completely unanticipated by me. So the lemma is that a two variable adjunction between the functors f, g, and h defines three parameterized adjunctions, one for each pair of bifunctors. This is one of these things where, I mean, depending on how you give the definition of a two variable adjunction, it just is three parameterized adjunctions. So I thought this was just going to be the matter of like forgetting some data. But what I wasn't anticipating are sort of subtleties involving opposite categories. So in pen and paper category theory, if I take a category C and I form its opposite, and then I form its opposite again, I have the category C back. But that is not what it looks like in MATLAB. So Ricardo sort of mentioned similar points earlier. So instead, what MATLAB knows about is something called an equivalence of categories between C, op, and C. And so the thing that was unexpectedly difficult here was defining the third of these parameterized adjunctions, which requires firstly flipping. So both stating the theorem and then proving the theorem seemed difficult. So to state the theorem, the sense in which the functors G and H are adjoint, first I need to flip the arguments. So these are functors of two variables. And rather than consider G as a functor from A op to C to B, I need to think of it as a functor to C to A op to B. That's pretty trivial. But then I need to precomposed H with this equivalence of C op and C. So rather than H being a functor from C to B op to A, it needs to be a functor from C op to B op to A, just to match the signature of this notion of parameterized adjunction. And then similarly for G, I need to op it, so replace both the source and target categories by their opposites, and then post-compose with some equivalence between functor categories involving opposites. And again, on paper, this just doesn't appear, but it stumped Gauss. Okay, so let's wrap up. So here's kind of what I think of the present status of autoformalizing category theory. So I would describe these challenges as sort of very easy in the sense of if Bhavik is racing the autoformalization agent, Bhavik will be able to do this within an hour. So the co-representability theorem I've formalized. It takes about 50 lines with all of the commentary. I'm sure I could get that down now that somebody's questioned why it takes 50 lines. But the point is, it's not something that's particularly difficult. So in the literature, this parameterized two-variable adjunction theorem, in a textbook I've written about category theory, I don't even include a proof because it's sort of just one of these follow your nose. These details are very bookkeeping. So what I would consider success for an agent formalizing this is not just giving me a sorry free file, but sort of mathlib accepted code. This is not, it's not really making a contribution to formal mathematics in Lean unless it's of high quality. This is not sort of a theorem that's, part of a larger research program. This is not something that I would be able to publish these formalizations in like the Journal of Formalized Mathematics. This is just some very basic, very traditional category theory that should be in the library and happens not to be right now. Okay, I mean, what I'm actually working on is a sort of infinite dimensional generalization of category theory called infinity category theory that is now also several decades old. So this category theory was maybe 50 years old. The infinity category theory is, 10 and 20 years old. And there are infinity categorical analogs of these theorems that we can't even state in MATLAB, sort of much less formalize. And, maybe with a lot of effort, we could state them, but then what would it take to formalize a surely unreadable proof? And I should say, I'm interested in this not so much because it's, I'm desperate to have these particular theorems in MATLAB, but this is blocking a lot of literature. So recent papers in the area will cite these results without proof. So the last thing I wanted to mention, and this is relates to something Leo mentioned yesterday, is it's not like it's completely impossible to formalize this mathematics anywhere. So outside of Lean, there's a proof assistant called RZK that has in fact formalize the infinity categorical version of the co-representability theorem. This is the entire proof here. It looks terrible because there's a sense in which RZK is a terrible proof assistant. We don't have implicit arguments. So I've written the name of the category like 10 different times in this proof. But will we ever be able to auto-formalize anything outside of Lean? Okay, I've taken too long. Thank you.
Thank you very much, Emily. Now we have time for, I would say, one question, maybe two if they're short.
Hi, thanks for the talk. So when you're talking about the issues with auto formalization and data here, I mean, it's even more than just producing data, right? Because if you're talking about MATLAB acceptable code, it's not even like completely obvious what that is. Because if like you look back historically, they're like 2019 or so or whatever of like we used to define categories not just in type but in sort, and like this is so sensitive to the meta theory definitions. And even if I'm in univalent foundations, I'm talking about if things are H sets or whatever. Like, so is there any way, I mean, I don't know if there's even much like training data for this of other areas that have these corresponding problems. Do you think there's any way that this producing data gets resolved in terms of this stuff that's so close to the meta theory?
Right. I'm not close enough to the development of these agents to know how these problems get resolved. I feel like my role here is in highlighting problems that I think need to be resolved in the future. if the results of this are really going to be usable by the mathematics community broadly. So sorry, no solutions, just problems.
Okay, thank you.
I think we had another question from Babik.
Thank you for the talk. It was very nice. You mentioned setting this challenge to certain agents. Do you have any results?
Yes. So I had somebody, I don't have access to alpha proof, but I had somebody at Google DeepMind run the first challenge with alpha proof, and it was not able to do anything at all. I guess you were there, so it wasn't able to do anything at all. I would like to run this challenge again, so if somebody wants to give me alpha proof access, I'm game. So both Aristotle and Gauss, the Math Inc. and the harmonic agents, were able to do the first challenge quite easily. And we're mostly successful on the second one as well, not giving MATLAB quality code, I would say, but in sort of auto-formalizing the statements and then giving proofs of them. I think what's still open is sort of what the correct auto-formalized statements ought to be, in the case that I particularly illustrated. I would also, the way I framed this challenge initially, I was talking with the Math Inc. folks first before talking with the harmonic folks, is that it's, I'm not going to consider this challenge over until this is in MATLAB, because I think people like me who are sort of mathematicians who are interacting with AI companies need to kind of be mindful of and the companies themselves need to be mindful of the entire progress. What we want the result to be is more formal mathematics that is usable by the mathematics community, and that means that it's not enough that it's in some random repository somewhere with a bunch of sort of ugly things that involve. I mean, there's there's classical written at the first line of kind of almost all of these proofs when none of this requires classical mathematics. So that's not good enough. We really need to complete the life cycle. I should say something that became clear from this experiments is that, kind of the user experience of interacting with the agents really matters. When Gauss got stuck at several points, I found it very difficult to help. I was doing a lot of manual lean formalization myself because that seemed the most efficient way to communicate with the agent. It was also sort of more difficult to trigger runs with the agent. When I was interacting with harmonic, it completely ignored the uniqueness step in the statement of the theorem about parametrized adjunctions and just gave the correct construction, but I was able to use the natural language mode to ask it to give me the uniqueness statement as well, and that's when it produced the auto-formalization there. So in the example that I illustrated with these auto-formalized statements involved by both Gauss and Aristotle, they both gave a proof as well. They're quite ugly because the statements are quite complicated. Those proofs will not be accepted by MATLAB, but there have been some success. So.
Thank you.